These are the answers to the AP Chemistry packet on topics 3.1 to 3.2. This is MCQ Practice, which means these are multiple choice questions for you to practice so you can prepare for the AP Chemistry exam. In the video description area, there is a link to the packet that accompanies this video. Now, let's take a look at our first multiple choice question. Question 1 says, data for the HF bond are listed in the table above. Which of the following provides the correct predictions for both the average distance between HF molecules in a pure sample of liquid HF and the energy required to break the attractive forces between HF molecules? So here on this slide, you can see a sample of HF molecules. Those black lines represent the covalent bonds in between the atoms and within individual molecules. These dashed lines represent the attractive forces in between HF molecules in a sample of HF. So the distance between the atoms within a molecule is shorter than the distance between the molecules in a sample of a pure substance of a liquid. So in general, the distance between the molecules, that is, an intermolecular attractive force, is greater than the distance between the atoms, that is, a covalent bond. Now, with respect to the energy, on this slide, you can see I'm highlighting an essential knowledge statement from topic 2.2. And so at first glance, you might think this doesn't belong in this particular video, because in this video, I'm talking about topic 3.1, intermolecular attractive forces. But take a look at that last statement in that section that I'm highlighting. It says, bonds with a higher order are shorter and have larger bond energies. So one way to interpret that sentence is that a double bond, for example, is shorter and has a larger bond energy than a single bond. So the general statement we can make with respect to attractive forces and the length of an attractive force as well as the energy required to break it is the following. In general, when you have a shorter bond or an attractive force, more energy would be required to break that. Whereas if you have a longer bond or attractive force, then less energy is required to break it. So we can apply that information to topic 3.1, comparing intermolecular forces with covalent bonds. We can say that the intermolecular attractive forces in between molecules are weaker than covalent bonds. So the energy required to break intermolecular attractive forces is less than the energy required to break covalent bonds. So now we can successfully answer question 1. So the bond length for the HF bond, again, that's a covalent bond between two atoms, is 92 picometers. We would expect the distance between HF molecules to be greater than that. So the correct answer to question 1 is either C or D, just based on the distance. Now, with respect to the energy required, it takes 565 kilojoules per mole to break the covalent bonds. It should require less energy to break intermolecular attractive forces in between molecules. So the correct answer to question 1 is C, greater than 92 picometers and then less than 565 kilojoules per mole. Now let's take a look at question 2. Question 2 says, data for carbon tetrachloride, CCl4, are listed in the table above. Which of the following provides the correct predictions for the properties of carbon tetrabromide, CBr4? Now, with respect to the shape of these two molecules, they are both tetrahedral, and based on the symmetry and the fact that all of the bond dipoles in those molecules cancel each other out, both CCl4 and CBr4 are nonpolar molecules. And the only type of intermolecular attractive force that they experience is London dispersion forces. And with respect to London dispersion forces, it's going to come down to the size of the electron cloud when we compare CCl4 and CBr4. So a chlorine atom has a total of 17 electrons, whereas a bromine atom has a total of 35 electrons. So on this next slide, this is information that I had presented in an earlier video for topic 3.1. Again, I'm focusing on London dispersion forces for these two nonpolar molecules. The strength of the London dispersion forces increases as the number of electrons in an atom or molecule increases. The larger the electron cloud is, the more likely that it is that the electron cloud can be distorted or polarized. In other words, the larger the electron cloud is, the more polarizable it is, and the stronger the London dispersion forces between the particles. Comparing the relative strength of the attractive forces between the particles helps us to make predictions about boiling points. The boiling point of a substance is related to the relative strength of the attractive forces between the particles. So we have CCl4 and CBr4. Now, the CBr4 molecule has a larger electron cloud. It's more polarizable. Stronger London dispersion forces exist in that particular substance. Therefore, we would predict that CBr4 has a higher boiling point. That means that in question 2, we can narrow down the choices to either B or D, because CBr4 should have a greater boiling point, greater than 350 Kelvin compared to CCl4. But what about the vapor pressure? So vapor pressure is a topic that's mentioned in one of the essential knowledge statements for topic 3.2. It says many properties of liquids and solids are determined by the strengths and types of intermolecular forces present. Because intermolecular interactions are broken when a substance vaporizes, turning from a liquid to a gas, the vapor pressure and the boiling point are related to the strength of those interactions. So on this slide is something I had presented in an earlier video for topic 3.2. And you can see on the left we have water at 20 degrees Celsius with a vapor pressure of 17.5 torr, and water's boiling point is 100 degrees Celsius. On the right, we have a sample of ethanol, which is also at 20 degrees Celsius. Now, its vapor pressure is actually 44.6 torr at that temperature, and its boiling point is 78 degrees Celsius. So the takeaway from this information is that when comparing two different liquids at the same temperature, the liquid that has a lower vapor pressure, like water in this example, will have a higher boiling point, or you could say it the other way around and it would still be true. The liquid that has a higher vapor pressure, which would be ethanol in this example, has a lower boiling point. Now on this graph of vapor pressure versus temperature, you can also see that comparison, that for ethanol, it has a higher vapor pressure at a given temperature and it has a lower boiling point, whereas water has a lower vapor pressure at a given temperature and has a higher boiling point. So now let's go back and finish the answer to question 2. We already know that CBr4, based on its larger electron cloud and greater polarizability, should have a greater boiling point than CCl4. And because of that inverse relationship between vapor pressure and boiling point, the correct answer to question 2 is B. A greater boiling point would be associated with a smaller value for vapor pressure at a given temperature. So the correct answer to question 2 is B, less than 90 torr for the vapor pressure and greater than 350 Kelvin for the boiling point. Now let's take a look at question 3. Question 3 says, the table above shows the structural formulas and molar masses for 3 different compounds. Which of the following is a list of the compounds in order of increasing boiling points? Now, before I go to the details of answering this question, let me just make a brief comment about molar mass. If this question were written as a free response question on the AP Chemistry exam, where you had to provide some sort of justification or explanation comparing the relative strength of the attractive forces and the boiling points, do not use molar mass as an argument or a justification or an explanation. So what I will say is that even though the molar masses are given, I'm not going to use molar mass as a justification or an explanation to compare. What I am going to do is talk about the relative strength of the intermolecular attractive forces. So the fact that I can look at acetone, 1-propanol, and butane and compare the relative number of carbon atoms, hydrogen atoms, and in some cases oxygen atom, I can say that all three of these substances have approximately the same size electron cloud. But again, I will not use molar mass in my argument. Now let's start with this particular compound, which is butane. It has a very symmetrical electron cloud such that all of the bond dipoles cancel each other out. So butane is classified as a nonpolar molecule and would experience only London dispersion forces between molecules of butane. The next molecule I'm going to take a look at is acetone. And I'm going to go ahead and redraw the acetone molecule just to highlight that trigonal planar geometry for that central carbon atom. Because the way that acetone was drawn on this table, it might lead you to believe that it's a very symmetrical molecule, and therefore you might think it's nonpolar. But in fact, acetone is a polar molecule. The bond dipoles in that molecule do not cancel each other out. We have a carbon-oxygen bond, and then we have two carbon-carbon bonds, but there is not symmetry in 3 dimensions that would create a nonpolar molecule. So if acetone is in fact a polar molecule, then in addition to experiencing London dispersion forces between acetone molecules, there would also be dipole-dipole attractive forces between acetone molecules. Now, you might be wondering, what about hydrogen bonding attractive forces in a substance such as acetone? Well, the requirements for a substance to be a hydrogen bond donor is that the substance should contain a hydrogen atom that is covalently bonded directly to either nitrogen, oxygen, or fluorine. And if we look at the details of the acetone structural formula, we can see that all of the hydrogen atoms in the acetone molecule are directly bonded to carbon. So therefore, in a pure sample of acetone, there are no hydrogen bonding attractive forces between acetone molecules. Now for propanol, it does have a hydrogen atom that is directly bonded to oxygen. So propanol, because of its asymmetry, is not only a polar molecule, therefore would experience London dispersion forces, as all molecules experience that, dipole-dipole attractive forces between molecules, because 1-propanol is polar, but it also would be able to experience hydrogen bonding attractive forces between molecules of propanol. So now that we've identified the types of attractive forces for butane, acetone, and propanol, and again, all 3 of these molecules are roughly the same size electron cloud, we can go ahead and identify the weakest intermolecular attractive forces, that would be the lowest boiling point, and then the strongest intermolecular attractive forces for the highest boiling point. So we'll start with butane. Butane has the weakest intermolecular attractive forces in this set of 3. And then 1-propanol has the strongest intermolecular attractive forces in this set of 3. So butane, followed by acetone, followed by propanol, those 3 substances are listed in choice B in order of increasing boiling points. So the correct answer to question 3 is choice B. Now let's take a look at question 4. Question 4 says, the structural formulas and boiling points for 2 different substances are shown above. Which of the following interparticle attractive forces are most responsible for the fact that substance number 2 has a higher boiling point than substance number 1? Now, the first thing I'm going to do is eliminate one of the 4 choices in this question. And when we go from a liquid to a gas, what we typically do is break intermolecular attractive forces. Those are the attractive forces between molecules. What we do not break are covalent bonds. So going from a liquid to a gas, we do not normally break covalent bonds to go from a liquid to a gas. So therefore, that is not an option in question 4. Now, the other three choices are London dispersion forces, dipole-dipole attractions, and hydrogen bonds. And if we take a close look at the structural formula of each of these molecules, we can see that they are both polar molecules because of the asymmetry of their structural formula. So they would experience London dispersion forces and dipole-dipole attractive forces between molecules. And you can see that there is a hydrogen atom directly bonded to an oxygen atom in each of these molecules. So in addition to London dispersion forces and dipole-dipole attractive forces, each of these substances would also experience hydrogen bonding attractive forces between the molecules. And so if they experience all three types of attractive forces, how do we answer question 4? Well, the significant structural difference between substance number 1 and substance number 2 is the following. Substance number 2 does have a larger electron cloud. And so what does a larger electron cloud mean when we're comparing these two substances? Well, as I had mentioned earlier in this video, the strength of the London dispersion forces increases with the size of the electron cloud. In other words, the larger the electron cloud is, the more polarizable it is, and the stronger the London dispersion forces between the particles. And so that is the correct answer to question 4. Because substance number 2 does have a larger electron cloud than substance number 1, then that would be the significant difference. So the correct answer to question 4 is London dispersion forces. Now let's take a look at question 5. Question 5 says, the structural formulas of 2 hydrocarbons are listed in the table above. Based on the information in the table, which compound has the higher boiling point, and why is that compound's boiling point higher? So when we look at the ethane molecule, which is C2H6, and the butane molecule, which is C4H10, we can see that they both have symmetry, such that the bond dipoles cancel out. So both ethane and butane are classified as non-polar molecules, which means the only type of intermolecular attractive force that they would experience would be London dispersion forces. So ethane and butane do not experience dipole-dipole attractive forces between molecules because they are not polar. And the hydrogen atoms are directly bonded to carbon in each molecule. Hydrogen is not directly bonded to nitrogen, oxygen, or fluorine, so neither of these molecules would experience hydrogen bonding attractive forces between their molecules. Now, based on that information, and then something I had mentioned in question 4, let's go ahead and eliminate 2 of the 4 choices in question 5. So starting with choice B. Choice B talks about the fact that one of the molecules, ethane, contains stronger covalent bonds, and it says more energy is required to break those bonds. We do not break covalent bonds when we convert these molecular substances from a liquid to a gas. And since we're not breaking any covalent bonds, we can eliminate choice B. And then as I had mentioned, there is no possibility to experience hydrogen bonding attractive forces. So taking a look at choice C, it says something about more opportunities to form hydrogen bonding attractions. So again, that's not possible. We can get rid of choice C. And so what it comes down to in question 5 is very similar to what I had mentioned in question 4, in that the molecule that has the larger electron cloud is more polarizable and would experience stronger London dispersion forces between the particles. So the butane molecule has a larger electron cloud than the ethane molecule. It's more polarizable. Butane would experience stronger London dispersion forces, and you would expect butane to have a higher boiling point than ethane. So the correct answer to question 5 is D. Butane should have a higher boiling point because its molecules have more electrons, resulting in greater polarizability and stronger London dispersion forces. Now, let's take a look at question 6. In question 6, it says the structural formulas of two different compounds are shown above. Which of the following identifies the substance with the higher boiling point and provides the best explanation for the higher boiling point? So the first thing I'm going to do is classify each of these molecules to decide if it's polar or nonpolar. Looking at the molecule with the structural formula on the left, there's definitely some asymmetry in that structural formula. The bond dipoles in that molecule will not cancel each other out. So that molecule on the left is classified as polar, which means that a pure sample of that substance will experience both London dispersion forces and dipole-dipole forces as intermolecular attractions between its molecules. Now, looking at the molecule on the right, there's also some asymmetry in that structural formula, which means that the bond dipoles do not cancel out. So that molecule on the right is also a polar molecule and would experience both London dispersion forces and dipole-dipole attractive forces between its molecules. Now let's take a look at the possibility of hydrogen bonding for each substance. Remember that the requirements for a substance to be a hydrogen bond donor is the substance must contain a hydrogen atom that is covalently bonded to either nitrogen, oxygen, or fluorine. And so in the molecule on the left, each hydrogen atom is directly bonded to carbon. So that substance on the left cannot experience hydrogen bonding attractions in a pure sample of that substance. It cannot form hydrogen bonding attractions with neighboring molecules of itself. The molecule on the right does have a hydrogen atom directly bonded to oxygen, so the molecule on the right can experience hydrogen bonding attractions. So in between molecules of that substance on the right, there would be hydrogen bonding attractions. And as I consider these two molecules side by side, what I notice is there is not a significant difference in the relative size of the electron clouds for these two substances. And so since there's not a significant difference in the overall size of the electron clouds, then the substance that should experience stronger intermolecular attractive forces is the one on the right, because in addition to London dispersion forces and dipole-dipole forces, that substance on the right can also experience hydrogen bonding attractions. So if I have to predict which substance is going to have the higher boiling point based on stronger intermolecular forces, it would be the molecule on the right should have a higher boiling point. That means that I'm narrowing down my choices to either C or D. And what I'm looking for is the presence of hydrogen bonding in my explanation. So the correct answer to question 6 is that the substance on the right, the CH3, CH2, CH2OH, is going to have the higher boiling point because hydrogen bonding attractions are present in that substance on the right, but they are not present in the substance on the left. Now, let's take a look at question 7. Question 7 says, the structural formulas and boiling points for two different substances are shown above. Each substance exists in the form of a liquid at 20 degrees Celsius. Which of the following identifies the substance with the higher vapor pressure at 20 degrees Celsius and provides the best explanation for the higher vapor pressure? So the first thing I'm going to do is classify each of these molecules as either polar or nonpolar, starting with substance number 1. I can see that that structural formula has a lot of symmetry. Everything is balanced, and all of the bond dipoles in that substance number 1 would cancel out. So substance number 1 is classified as a non-polar molecule because of the symmetry of that structural formula. Therefore, substance number 1, being non-polar, can only experience London dispersion forces as attractive forces between neighboring molecules. Now, for substance number 2, that structural formula is asymmetric, so it's not balanced. That means that substance number 2 is definitely classified as a polar molecule. All of the bond dipoles in substance number 2 are not going to cancel out. So a polar molecule can experience both London dispersion forces and dipole-dipole attractive forces between neighboring molecules. Now, we already know the boiling point information. We know that substance number 1 happens to have a lower boiling point. That's because it has weaker intermolecular attractive forces. I'll remind you of something I had mentioned earlier in this video when I was talking about question 2, this inverse relationship between the magnitude of the boiling point and the value for the vapor pressure at a certain temperature. So a substance that has a higher vapor pressure at a given temperature should also be the liquid that has a lower boiling point. And so we know that substance number 1 has a lower boiling point, so it should have a higher vapor pressure at 20 degrees Celsius, and it has weaker intermolecular attractive forces. So the correct answer to question 7 is substance 1, which means the answer is either A or B, but I'm looking for an explanation that involves that difference in the relative strength of the attractive forces. Substance number 1 experiences only London dispersion forces, whereas substance number 2 experiences both London dispersion forces and dipole-dipole attraction. So the correct answer to question 7 is choice B. Now, let's take a look at question 8. Question 8 says equimolar amounts of 3 different gases are placed in identical rigid vessels, each fitted with a movable piston. The pressure of each gas sample is increased by moving the piston downward while the temperature is maintained at 25 degrees Celsius. This process continues until condensation occurs. Which gas sample, if any, should condense at the lowest pressure value? Now, let's go ahead and consider what happens as we move the piston downward in these rigid vessels. So as the piston is pushed downward, the gas pressure increases. And the gas pressure continues to increase until the particles of gas condense into a liquid. So condensation will occur when the gas particles experience sufficient attractive forces that cause the particles to stick together. So suppose as I'm increasing the pressure on all 3 of these identical rigid vessels, suppose that only one substance condenses while the other 2 samples have not yet condensed. As the pressure is gradually increased, the first gas sample that condenses into a liquid must be the sample that experiences the strongest intermolecular attractive forces. So if I say that in a slightly different way, the sample that condenses at the lowest pressure value must be the sample that experiences the strongest intermolecular attractive forces. Now we have 3 substances, and they are CH4, C2H6, and C4H10. These are all very symmetrical molecules, and because of that symmetry, they're all going to be classified as nonpolar. These are nonpolar hydrocarbons. That means that the only intermolecular attractive forces that they would experience are London dispersion forces. And as I've mentioned earlier in this video, the relative strength of the London dispersion forces is going to be affected by the overall size of the electron cloud. So taking a look at each of these substances, hopefully you can see that C4H10 has the largest electron cloud. Therefore, it would be the most polarizable of these three substances, and therefore C4H10 would experience the strongest London dispersion forces. So the correct answer to question 8 is choice C, because C4H10 has the strongest intermolecular attractive forces, then it would be the gas sample that would condense at the lowest pressure value. Now, let's take a look at question 9. Question 9 says, based on periodic trends and Coulomb's law, which of the following cations is most likely to have the strongest interactions with nearby water molecules in an aqueous solution? So before I answer this question, I'll show you a very similar question that I had talked about in an earlier video for topic 3.1. This question has to do with ion dipole forces. Ion dipole forces represent an attractive force between an ion and a polar molecule. They usually occur in a solution when an ionic compound is dissolved in a polar solvent, such as water. Coulomb's law can be applied when comparing the relative strength of an ion dipole attractive force. The attractive force between an ion and a polar molecule should increase as the magnitude of charge on the ion increases, that is the numerator portion of Coulomb's law, and as the size of the ion decreases, that's the denominator portion of Coulomb's law. So in this question from an earlier video, the correct answer was the sulfur 2- ion, and here's the process of narrowing it down. First, I focus on either the sulfur 2- ion or the tellurium 2- ion because they have a greater charge magnitude. So the greater the charge magnitude on the ion, the stronger the attraction between the ion and the polar water molecule. And then now that I've narrowed it down to either the sulfur or the tellurium 2- ion, I picked the sulfur ion because if the ion has a smaller ionic radius, then there is a smaller distance between the ion and the polar water molecule, resulting in a stronger attractive force. Now let's go ahead and use that same strategy to answer question 9. So we have 4 different cations. +1 or +2? Well, I'm going to focus on +2, so I'm going to eliminate choices A and B, because the greater the charge magnitude, the stronger the attraction between the ion and the polar water molecule. And so now that I've narrowed it down to either magnesium 2+ or strontium 2+, because of the greater charge magnitude, let's focus on the size. So the general trend in atomic radius on the periodic table is that size increases as you go from top to bottom down a group. So there's magnesium and strontium, they're in the same group, but magnesium is smaller in size than strontium. So because magnesium 2+ has a smaller ionic radius than the strontium 2+ ion, the ion with the smaller ionic radius has a smaller distance between itself and the polar water molecule, resulting in a stronger attractive force. So the correct answer to question 9 is C, the magnesium ion. It's because it had a greater charge magnitude than the ions in choices A and B, and it had a smaller ionic radius than the strontium 2+ ion in choice D. Now let's take a look at question 10. In question 10, it says 3 different substances were studied in the laboratory and the data in the table above were collected. Based on the data, which of the following most likely represents the type of bonding present in each substance? So the first thing I'm going to focus on in this data table is the property of electrical conductivity. We can see that substance Z is not a conductor of electricity in the solid phase, but it is a conductor of electricity in the liquid phase. And now, as you'll see on this slide, this is information that I had presented in a video when I was talking about topic 3.2. And what you're seeing on this slide is a table where I'm looking at different properties of the 4 types of solids. And those 4 types of solids are ionic, covalent network, molecular, and metallic. And so what's highlighted on this slide is the property of electrical conductivity for a metallic solid. So a metallic solid does conduct electricity as a solid because of the mobile valence electrons that can move and flow and conduct electricity. An ionic solid does not conduct electricity as a solid because the ions, the charged particles, cannot move freely. So an ionic substance does conduct electricity when melted or dissolved in a solvent because then the ions, the charged particles, can flow and move freely. So now take a look at substance Z. Because it is not a conductor of electricity in the solid phase, that means that substance Z is not a metal. Let's go ahead and eliminate choices A and C because we know that substance Z is not metallic. Instead, substance Z is an ionic solid because it is able to conduct electricity in the liquid phase or when it's melted. Now the next thing I'm going to focus on is the difference in melting point for substances X and Y. So we have to decide how that difference in the melting point helps us classify one of them is either going to be molecular or network covalent. So here on this slide, you can see a side-by-side comparison of covalent network and molecular. Focus on the attractions between the particles. So in a covalent network solid, there are covalent bonds between atoms in a large extended network. Very strong attractions, as in the covalent bonds between the atoms, that would lead to a relatively high melting point. On the other hand, with a molecular solid, there's relatively weak intermolecular attractive forces between the molecules, leading to a relatively low melting point. So relatively low melting point for a molecular solid, relatively high melting point for a covalent network solid. So now we can answer question 10. So because substance X has the lower melting point, it is more likely to be a molecular solid with relatively weak intermolecular attractive forces. And then substance Y, with the higher melting point, is more likely to be a covalent network solid with strong covalent bonds in that extended network. So the correct answer to question 10 is choice D. Now let's take a look at question 11. Question 11 says, a sample of a hard solid binary compound at room temperature did not conduct electricity as a pure solid, but became highly conductive when dissolved in water. Which of the following types of interactions is most likely found between the particles in the substance? So as I had mentioned when I was talking about the answer to question 10, an ionic solid does not conduct electricity as a solid because the ions cannot move freely. But an ionic solid does conduct electricity when either melted or dissolved in a solvent because the ions can move freely. So in this question, question 11, the answer is ionic bonds. So an ionic substance does not conduct electricity as a solid, but becomes highly conductive when dissolved in water. Now, let's take a look at question 12. Question 12 says, which of the following could be the identity of a white crystalline solid that exhibits the following properties? It melts at 320 degrees Celsius. It does not conduct electricity as a solid. It conducts electricity in an aqueous solution. So question 12 is very similar to question 11. Remember that in question 11, if something did not conduct electricity as a solid but became conductive when dissolved in water, that's an ionic substance. But now what we have to do is recognize which one of these 4 chemical formulas would exhibit ionic bonding. So take a look at this slide. These are the 4 types of solids: ionic, covalent network, molecular, and metallic. And I'm showing you at the bottom of this slide some examples of each of the 4 types of solids let me go ahead and talk about the general features of how you can recognize the type of solid by looking at the chemical formula. So, starting with an ionic solid, we have lithium bromide, sodium nitrate, magnesium oxide, potassium chloride. So what you're looking for would be typically a metal and a nonmetal, or something you recognize to be a positive ion and something you recognize to be a negative ion. So there could be some polyatomic ions like nitrate or sulfate in that formula. Now, for the covalent network, what I normally tell my students is go ahead and memorize this relatively short list of examples of covalent network solids. That includes diamond and graphite, which is carbon, silicon, so Si for silicon, quartz, SiO2, silicon carbide, SiC, and boron nitride, Bn. Again, a relatively short list of examples of covalent network solids. And now for molecular solids, those are generally composed of nonmetals, such as carbon, hydrogen, oxygen, the halogens like chlorine and iodine, sulfur, phosphorus, and as long as there's no recognizable polyatomic ions in that formula, then that would be a covalent, bonded, or a molecular solid. And then finally, metallic solids are, in fact, metals, such as sodium, magnesium, aluminum, nickel, copper, zinc, and so forth. Let's go ahead and take a look at our 4 chemical formulas here in question 12. So starting with choice A, that substance, C6H12O6, is composed of only nonmetals. That happens to be the chemical formula of glucose, and that would be a molecular solid. Nonmetals bonded in a covalent way, no polyatomic ions in that formula. Let me go ahead and skip to choice C. That's quartz or silicon dioxide. That's an example of a covalent network solid that you should be able to recognize. And then in choice D, it just says the symbol Pt, which is the element platinum, and platinum is one of the examples of metals on the periodic table. Now, coming back to choice B, we have sodium hydroxide. Sodium is a positive ion. Hydroxide is a polyatomic ion that has a negative charge. So that is an example of an ionic substance. Again, ionic substances do not conduct electricity as a solid, but they do conduct electricity in aqueous solution. So correct answer for question 12 is choice B. So question 12 is the last question in this packet. I hope that you found all of these answers and explanations helpful. Thanks for watching.